Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. In just a minute, I'll be thrilled to roll out this week's seminar with Senrui Chen. And I'm so glad that you joined us on time. Before we begin with introductions, we give everyone just about a minute or two to tune into the live stream. Meanwhile, folks, one of my favorite questions, which is where is everybody tuning in from today? You can reply to that in the comment chat box on YouTube, which is where you can ask myself and Senrui questions during the talk, as well as a place where you can discuss things with each other. In fact, if you want another question today, I've been thinking about where does the power of quantum computing come from? So feel free to offer your thoughts and opinions on that in the comment chat box, and we can have a nice chat. Some of that, I think, will tie into today's talk with Senrui about learning and learnability of quantum noise. To remind everybody, the seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel, so you can always go back, catch up on anything you missed. But you can only ask questions here live now during the seminar. So folks, I think with that, it's a great time to get to it. Today, I have the pleasure and privilege of rolling out for you the latest episode of IBM Seminar Series. I'm your host, Latko Minov, and I have the pleasure of having Senrui Chen from the University of Chicago and Liang Zhen's group, who will speak on the learnability of quantum noise. Senrui is a graduate student at UChicago, advised by Professor Liang Zheng. Senrui obtained his bachelor's degree from Tsinghua University in 2020, and his research interests include quantum device characterization, benchmarking, advantage mitigation, and many more things, some of which we'll hear about today. Senrui, it's great to have you here in the seminar. How are you today?
Hi, Doctor. Thank you for the introduction. I'm good. How are you?
Great. Well, it's a pleasure you accept our invitation. I'm going to hand it over to you, and the stage is yours.
Yeah. Okay. Thank you. Good morning, everyone. And it's a pleasure of me to have this chance to talk about our recent work about the learnability of Pauli noise. I'm Senrui Chen. I'm from UChicago. And this talk basically based on the joint work with Yunchao Liu, Matthew Otten, Aliris Asif, Bill Pfefferman, and Liang Jia. And I want to especially thank Yunchao Liu, my co-author, for help preparing many part of these slides. Okay, so let's jump right in. Yeah, so here's the outline of today's talk. I'll first give some introduction and talk about the theory of learnability of Pauli noise. Then I'll talk about some experiments we did on actually IBM's online quantum computer. And then I'll provide some outlook. So let's jump right in. So we're now in the NISQ area, where NISQ basically means noisy intermediate scale quantum. That means that we have already have the ability to build some small scale quantum computers and to make with many different physical platforms like superconducting circuits, trapped ion, Rydberg atom, and photonic chips. And we will see that many of these small-scale quantum computers start to demonstrate some kinds of preliminary proof of principle quantum advantage, or some proof of principle quantum algorithm. But one thing that we definitely, our current power of quantum computing have not reached the stage that really give us really strong practical advantage. And the question now is, what hinder quantum computer from exploit full power and to give us a very large quantum advantage? Well, at least for the NISQ area, the biggest challenge is about quantum noise. Noise is everywhere in today's quantum computers, and without the ability to characterize the noise and reduce the noise, we cannot really scale up quantum computer or to exploit full power. And I would recommend this recent talk, The Importance of N in NISQ by Joe Martinez at the KITP NISQ conference. And you can, if you're interested in that, you can find it in YouTube, which really talk about how important is quantum noise for the NISQ area. Okay, so my topic today will also be related to noise, and more precisely, we'll talk about quantum noise characterization, which means how to learn about noise in quantum devices. So this figure is from IBM Quantum, and this shows a 27 qubit devices of IBM's. Basically, you can show that there are many parameters about the noise. So I believe in if you look at these parameters, like the C0 error is something like around 1% or something. And knowing that what is the strength of the noise on our system, on our current system, can really let us estimate what is the what is the power of our current devices, and it will also be beneficial in other ways. Okay, so basically, why do we want to do noise characterization? Well, there are several reasons. We need to learn about the noise in order to, for example, further reduce the noise via calibration or improve our hardware. Or we can use the knowledge of the noise to perform error mitigation in near-term experiments. And we can even use the knowledge to design suitable error correction strategies for tolerant quantum computing. So basically, since goes like we first do noise characterization to obtain knowledge about the noise, and then we can use the knowledge to reduce the noise. In this work, we are especially interested in learning noise of quantum gates. If we look at the state of the art, we in many of the platforms, the single qubit gates are relatively good, and at least on the IBM's data, we can see that it typically has 10 to the minus 3 to 10 to the minus 4 error rate. But the 2 qubit gates are really the noisy one, and so we'll be interested in characterizing the noise of 2 qubit gates in general. But noise characterization is really a challenge in the quantum world. So there are several challenges we can discuss. The first about is the reliability. Basically, we want to characterize the gate with imperfect state preparation and measurements, which we call this spam or spam error in short. And the spam error in current devices, I would say it is typically comparable to the order of the gate noise. So we really cannot just ignore the spam error. If we do that, we cannot get a reliable characterization of the gate noise. On the other hand, we want our characterization of noise to be informative, which means that we might want more knowledge about the noise. For example, we want to know what kind of noise, the individual error rates of a specific kind of noise, instead of just obtaining a single fidelity parameter from randomized benchmarking. And finally, we want the characterization to be scalable. For example, we want to benchmark large quantum system, like 50 to 100 qubits with manageable efforts. And this will require us to make some simplification, but also we want to make our simplified noise model to be reasonable. Well, in today's talk, we'll focus on a specific noise model, which is called a Pauli noise model, where noise are modeled by Pauli channels. And Pauli channels are basically a stochastic mixture of Pauli operators. As a very simple example, let's consider a single qubit with a 5% bit flip noise. And this kind of noise channel can be modeled by this map. Basically, there are 95% of chance the state does not change, but a 5% chance there was a Pauli X applied on the state. And we can see that if we write down the probability of different Pauli appears as a probability distribution, we call it the Pauli error rate. We will say that Pi equals to 0.95, Px equals to 0.05, and Py and Pz equals to 0 because there will not be Y and Z Pauli operator applied here. So this is just a very simple example of Pauli channel. Why we care about this kind of Pauli channel? Why we care about this kind of Pauli noise? Well, there are many reasons. First, Pauli channel can describe a very wide range of incoherent noise. For example, dephasing noise, depolarizing noise, and also the bit flip noise we mentioned here. And also, for general noise that are not necessarily Pauli, there are some techniques to engineer the noise into Pauli noise, which is called randomized compiling, and I will talk in 2 slides. And finally, it has been shown that if we have knowledge about the Pauli noise, we can use it to do error mitigation and even design like better error correction codes. So for the error mitigation part, I think this recent work, I think Zlakto has a very, very good talk on that. And if you're interested in how to use like Pauli noise model to do error mitigation, you can check out Zlakto's talk or this archive paper. Yeah. And now let's define Pauli channel more rigorously. If we consider n qubit Pauli channel, it can be written in these two equivalent form. Let's look at the first form. Basically, the first form is showing that basically a Pauli channel is just a probability application of n qubit Pauli operator, where the big PA is just n qubit Pauli operator, which basically is a product of single qubit Pauli operator. And the small PA here is a Pauli error rate, which is the 4 to the n dimensional probability distribution. And with some effort, you can show that every Pauli channel can also be written in this form. How do we say that? Basically, you can, because we know that the Pauli operator span all the space of all possible density matrix. So basically, you can expand any density matrix in the basis of Pauli operators. And with this, you can show that every Pauli channel can also be written in this equivalent form. And in this case, it will be parameterized by a 4 to the n dimensional vector lambda, which is known as the Pauli fidelities or Pauli eigenvalues. The reason why this is called a Pauli eigenvalue is also very obvious. If you put a Pauli operator PB into this Pauli channel, you will see that the output will still be proportional to PB. It just pick up a phase, or not a phase. It will pick up an eigenvalue. And in the case that there's no noise, lambda b will be 1. In case there is some noise, lambda b might be smaller than 1. So this lambda b really hints like the fidelity of the Pauli channel. The two parameterization, Pauli error rates p and Pauli fidelities lambda, are related by a so-called Walsh-Hadamard transform. The detail is not important here. I just put it here for completeness. Basically, it's like some kind of Fourier transformation. And just give you a very simple example. In the previous example of Pauli error rate 0.95, 0.05, and 00, if we compute the Pauli fidelity, it'll be 1, 1, 9, 0.9, and 0.9. Basically, the Pauli fidelity, if you input a Pauli I or Pauli X, the channel will preserve the Pauli. But if you input Pauli Y and Pauli Z, it will like only have like 0.9 fidelity or something. And finally, I want to talk about the degree of freedom of a Pauli channel. And you can easily see that because there are 4 to the n independent parameters, the degree of freedom will be 4 to the n minus 1. Because there's a 1 degree of freedom that is trivial. You can see that the Pauli fidelity related to the identity, and also the sum of all the Pauli error rate is equal to 1. So the degree of freedom is only 4 to the n minus 1. Yeah. Yeah, so here's some basic about Pauli noise. Go on, and please interrupt me if there's any questions. Okay, and yeah. Okay, and here is about a technique called randomized compiling, which is the techniques to make a general noise model into Pauli noise. Let's see how it works. So if we consider a quantum circuit that consists of interleaving layers of, first, single qubit arbitrary unitary gates, and second, multi-qubit cleaver gates. So it will look like this. They have some arbitrary single qubit gate. Note that the single qubit gate can be non-cleaver. You can use T gate or any other non-cleaver gate. So this gate set is really can do universal quantum computing. Now, if we assume that the single qubit layer have negligible noise or have some like gate independent noise, then one thing we can do is that we can randomly inserting Pauli gates into the circuit in a way that does not change the logic of the circuit. And if we do that, then the noise attached with the multi-qubit cleaver gate will be turned into a Pauli noise. Yeah, let's look at the figure. Basically, in this original circuit, you can input some random Pauli here, and you can compute that how to insert another layer of random Pauli here, such that in the case that the signal is perfect, these two layers of Pauli will like perfectly cancel. And yeah, And after you insert multiple layer of random polys, you can combine the layer of single qubit gate into only one layer of gate. So these techniques will not increase the depth, but it will turn every noise into a poly noise. And here I want to mention that the spam noise will also be turned into a poly noise. And these techniques can be like, say, in this paper. So basically, this gives us a reason why we need to care about poly noise. So now we see that for general CBTP noise, we can use techniques of randomized compiling to put into a poly noise. So for example, in this figure, if we apply a CNOT gate, and we assume that each time we assume this gate, there will have some imperfection indicated by a channel attached to it. Now, basically, we can assume that this is a poly channel attached to it. And mathematically, a noisy implementation of a Clifford gate G can be written as G concatenating with a poly channel lambda. Now, let's define the task that we are concerned in today's talk. We want to learn the poly noise channel lambda attached to a specific Clifford gate G under unknown spam noise. Here, by learning the poly channel, basically we mean if you can either learn the poly error rate or the poly fidelity of the channel, then you complete this task. But here comes the question, is this task even achievable? I mean, with standard assumption, is this lambda really learnable? Here by standard assumption, I mean, for example, we can ignore single qubit gate noise, and we can assume the total gate noise is small, and we assume the noise is Markovian and time stationary. But crucially, we have two assumptions, important assumption that we want to do the learning under unknown spam noise, unknown state preparation and measurement noise. And also the noise, we assume the noise gate dependent. That is, for different Clifford gate, it can induce different kind of noise. So with this assumption, one question to ask is whether lambda is learnable. It turned out that this question is an open question, even for a single CNOT gate. And basically, the main contribution of our work is to provide an answer to this question. Yeah. And before I jump into the theory, is there any questions?
Thanks, Senrui. There was one or two questions in the chat, but I think other people answered them in there, that clarification-wise. So this is great. You're very clear. Go on.
Okay, great. That's very good. Thanks for answering, for those who answered the questions and for those who asked the question. So let's jump into the theory part. Okay, so we talk about the issue of learnability. What does the word learnability mean? So in the next few slides, we'll try to explain this in more detail. So there are actually some intrinsic symmetry in a quantum system that is known as gauge freedom, which basically is the origin of unlearnability. Let's just say a very simple example, and we'll understand what does this mean. So let's consider a quantum system, a very trivial quantum system. We only noisy state preparation and noisy measurement. Now we do the following things. We prepare a cat zero state, and we measure in the computational basis. And it turned out that we see the outcome 1 with probability 5%. So this means that there is some error going on. But but if we think of what really happened here, there are several possibilities. For example, it could be the case that all the 5% of noise come from the state preparation, and the measurement is perfect. It also could be the case that the 5% of noise all come from the measurement, but the state preparation is perfect. And it also could be like around 2% is come from the measurement, and around 3% is come from the state preparation. The key is that you cannot really tell the difference between these three cases. Here, let's just assume the noise is some kind of depolarizing noise. So basically, there's no way for you, because you can only do the separation and do the measurement. There's really no way of you to distinguish between these three cases. And like more generally, you can think of there's a continuous manifold, and each point in the manifold represent a possibility of the noise model. So on the leftmost hand side, the state preparation is contribute all the noise. On the right-hand side, the measurement contribute all the noise. And for any point in this continuous manifold, if you move from one point to another point, basically this will not change any experimental outcome. So an operation basically move from like one instance of noise to another instance of noise within the gauge is called a gauge transformation. And basically this is discussed in the theory of gauge set tomography. Okay, so let's do it more specifically. So in our setting, we'll consider that there's some, so basically in our quantum system, we can prepare some initial state, we can conduct some POV measurement, and we can apply a gauge set of gates, but they are all subject to some unknown quantum noise, N. Here I use N to denote like the collection of all the parameters of noise. Now let's consider a general form of gauge transformation, which can be written in this form. It will be much more clear because I will show a figure later. But basically, you'll see that this is a transformation defined by any invertible linear map M, and it will change all your initial state POV measurement and the gate. And if we consider two noise model that can be related by a gauge transformation, then we call them indistinguishable. The reason is that there's no way for them to be distinguished because they will produce exactly the same statistics in any quantum experiment. So let me be more clear here. Let's think that we have a quantum experiment. We want to prepare some state rho, and we apply two quantum gate, G1 and G2, and at the end, we measure the POVM and we see the result EJ. So the probability that we see the result EJ basically can be written as trace EJ times G2 concatenate with G1 acting on state rho, right? And now let's assume that we have some invertible linear map M, and we insert M and M inverse into the circuit like this, right? And you immediately see that this will not have any observable effect because M and M inverse, you can just cancel them, right? So basically, but now let's think that we reorganize the figure as follow. So now we define this rho going to M acting on rho as a new initial state. We call it rho prime, and the two gate is redefined in this way. It's called G1 prime, G2 prime, and the POVM element is also redefined as EJ prime. So if you think of a noise model that instead of, so when you want to prepare rho, E, and G, it is instead prepared as rho prime, G prime, and E prime. You immediately say that in any experiment, the probability distribution cannot be distinguished from this one, right? So this is the reason why this will give you a valid gauge transformation. Okay, and finally, because we want to learn information about the noise, so we can consider a function, any function of the noise, which can be written as Fn. And we call a function of noise to be unlearnable if it takes different values at two indistinguishable noise model, right? This is also like quite straightforward. If you have two like different noise model, they're actually indistinguishable. No way for you to distinguish them. But you consider a function that take different value on two indistinguishable noise model, then we can call this function unlearnable. Otherwise, if a function like for any indistinguishable, let me see. Well, if you cannot find two indistinguishable models that have different value of f, then we call f to be learnable. And also, let's see an example. See the simple example we just discussed. The noise model with just state preparation and measurement. In this case, what is the learnable function? Well, the total strength of the state preparation and measurement, roughly speaking, is state preparation plus measurement, is something that is learnable. Because if you're moving along the gauge, the manifold of gauge, the SP plus M is just really something not changed, just 5%. So that is something we call learnable. However, either separation noise or measurement noise itself is individually, we call it unlearnable, right? I see. I hope this is clear. You can ask a question later. But our goal here is basically so our goal of this work, we want to do this kind of classification of learnable function for general Pauli noise model.
Do you want to maybe motivate for us the part? So if there is this gauge of freedom, then and you can't distinguish it, then does it actually matter for anything, or when does it matter?
Yeah, that's a good one. I have a slides for that, and I will go there immediately. Yeah, thanks for the point this out. Yeah, yeah. Actually, this slide is about question about learnability. But before that, let me just finish these slides. Basically, our goal is that for the space of all function about the noise, we want to classify the function into learnable part and unlearnable part. And if a function is learnable, basically that means that the function is invariant under any gauge transformation. And this also implies that we can find the algorithm to learn it. And if the function is unlearnable, which just means that it would be variant under some kind of gauge transformation, and then we cannot hope to find any algorithm to learn the function. Yeah. Okay. So
Wait, sorry. You're saying that it makes a difference. Sorry, the learnable piece is the one you're saying it's unvariant under a gauge, and now I'm confused. Isn't it the other way around, that if you see a difference in the effect of the function, then you learn? Sorry, maybe clarify that again.
Yeah. No. So it's like it must be invariant under gauge transformation for it to be learnable. This is because, so if you just look at this example, you can see why. Because the separation noise will change around the gauge transformation, and this will make it unlearnable because it's like not well defined in some sense. Not the correct. No, I shouldn't say this way.
Okay, I see. Well, yeah, I see. I think I see what you mean. Yeah, because then you maybe
yeah. And you see that separation plus m is like something invariant on the gauge transformation. Yeah, good. So there must be many questions about our definition, this definition of learnability. But let me just address, I think maybe the most prominent one, and then people can ask more. I think one question people can ask is like, is unlearnable function physically relevant, or if a function is unlearnable, do we need to care about it? Well, here's my answer at least. I think there are two kinds of goals for quantum noise characterization. One kind of goals might be hardware side. That is, we want to use the information of noise to calibrate devices parameters or to upgrade our designs. And another part of the purpose may be, algorithm side. We want to use the information to improve the performance by using error mitigation or error correction. And these two goals actually will make a difference. If we focus on goal one, we actually want to do a full noise characterization. I mean, even if the noise is unlearnable, we still want to learn it. For example, an experimentalist will really want to distinguish state preparation noise from the measurement noise. Because if we know that, we have a bad state preparation, then maybe we'll try to come up more clever ways to prepare the state. If we have a bad measurement, then we try to come up with a very good method to improve the measurement. In this sense, if something is unlearnable, then this is the bad news. However, if we are focused on goal two, that is, we only care about the performance or observable effect. In this sense, we don't really need to care about unlearnable information, because if a function is unlearnable, then there's no way to observe them, and this means that you ask the wrong question. But however, you still, I would argue that you still need to know what are learnable, because this will help you to design method to actually learn them. So I would recommend this recent paper also by Robert Huang, Steve Fleming, and John Preskew, talking about foundations for learning from noisy quantum experiments. In their paper, basically, I think they classify this goal 1, 2 is one is called the intrinsic characterization, the other is called extrinsic characterization, and there will be a difference. Yeah, please let me know if that makes sense, or if there are any other question about learnability.
Yeah, maybe a quick question. And suppose we have 2 qubits and we learn some C0 gate, and you're saying that the noise on some C0 gate, you're saying, well, I also kind of need to separate that from the spam, and I'm still, sort of stuck on having this gauge degree of freedom. Or maybe I guess you'll get into this more in the next slides. Will that then matter for something like using that knowledge about the noise in like a probabilistic error cancellation scheme with this gauge?
Yes. You mentioned it, like this is the problem you mentioned to me like earlier, right? I would say that, so in the most general case, let me see. So at least in the most general development of all this theory, if a function is unlearnable, this really means that it does not have to have any effect that is observable. But for the part of maybe it's helpful to clarify this point. So in this whole work, we only consider about basically function of gate noise. And if you are thinking about like error mitigation or quantum or probabilistic error cancellation, you actually of not only the gate noise, but also the separation noise and the measurement noise. So in that sense, I think our characterization does not directly apply there. So it's like the function f here. We are working with function only of the gate noise. But in order to understand that for quantum error mitigation, you need to consider function of both the gate noise and the spam noise. So that's the reason why the theory here does not directly apply to solve the issue for error mitigation. That's my answer for now, I would say. Maybe we can.
Okay, thanks. Maybe I'll revisit it later. Thanks.
Yeah. So are there any question? Any question else?
Well, go on, thanks.
Okay, great. Great, so now we can get back to the task. So now let's revisit the task. We have already assumed randomized compiling, so every noise is Pauli. The task is to learn the gate-dependent Pauli noise under unknown spam noise. Let's start with a very simple example. That is, we want to learn noise of a single C0 gate. So C0 is a 2-qubit gate, so there will be a like 16 degree of freedom, and one of them being trivial, so there's actually only 15 degree of freedom. So, or more explicitly, we just want to learn the 16 Pauli error rate or the 16 Pauli fidelities. But how do we want to do that? Because now we have unknown spam noise. The separation and measurement also subject to some noise channel. Can we, in this sense, how can we learn this number? Well, we can use the idea from randomized benchmarking. I won't discuss about the detail of randomized benchmarking, but only hint on the key idea. Basically, in the randomized benchmarking style, the family of randomized benchmarking protocol, the idea is that the spam noise only appear once, but the gate, you can apply it many, many times. So there's the asymmetry. You can use this asymmetry between spam and the gate to learn about something like the average gate fidelity in a spam robust way. But here I want to mention that in order to do this, you really need some kind of randomization to ensure that the gate has some incoherent condition of noise. Okay, to be more specific, in a typical randomized benchmarking experiment, it's like this. If you want to characterize some gate, you repeat it 4 times, 3 times, 5 times, and 7 times. And for each time, you can experimentally plot the probability that some kind of fidelity measure, and this fidelity measure will decrease exponentially according to the number of gates you concatenate. And then by extracting the decay rate or the slope of this stuff, you can estimate the noise of the gate in a way that is independent of the spam. Can we use a similar idea to learn Pauli noise, Pauli error rate? Well, this is doable. At least one of the methods to do that is using cycle benchmarking, which is the protocol proposed in this paper. Cycle benchmarking is a variant of randomized benchmarking used to characterize a specific multi-qubit Clifford gate. And the circuit will something look like this. Basically, the reason why it's called a cycle benchmarking is like we assume that in our system there are many clock cycles. In each clock cycle, we'll apply 1 layer of single qubit Pauli gate and 1 layer of multi-qubit Clifford gate to be characterized. And yeah, so there are some advantage of using cycle benchmarking. The first is that it is spam robust, and it's easily implementable because you can see that the separation and measurement only using single qubit gates, and you only need to consider specific multi-qubit Clifford gate instead of implementing the whole Clifford group like in RB. And also, it only assumes that you have good single qubit gate. In contrast, standard randomized benchmarking actually requires a condition called gate independent noise for the whole Clifford group, which is like a really hard condition to satisfy. And also, the cycle benchmarking can be used. The original cycle benchmarking is only used to characterize the fidelity of a gate, but it can also be easily generalized to learn individual Pauli fidelities. However, up to some degeneracy. I'll talk about what I mean by up to some degeneracy. I think the best way we do that is we jump right in to see a specific example of cycle benchmarking. So in this example, let's see how do we characterize a single C0 gate using cycle benchmarking. So the circuit will be something look like this. There are some state preparation and there are some measurement. And in the circuit, this box is for some random Pauli gate. And this one is for C0. And here we just explicitly write out the noise channel lambda attached with C0. And here we assume lambda to already be a Pauli noise channel because this can always be ensured by randomized compiling. And this example shows a depth 3 example. And you can imagine that we can concatenate 4, 5, 6, 7, blah, blah, and yeah. Very similar to RB, we can extract the slope. Our goal is to learn the 16 Pauli fidelity of lambda. Let's see how we do that. So here, let's start with lambda ix. Let's see what will happen if we input a Pauli operator ix to the circuit. Yeah, this is like, at least mathematically, it makes sense. You just view as a whole circuit as a channel, and you can always act the channel on the Pauli observable. So let's do this first. If we have an ix input here, the first step is that the ix will go through a layer of Pauli operators. Pauli operators will not change Pauli operators, just give them some phase, plus or minus. And from now, we'll just ignore the sign because the sign can always be like corrected afterwards. Sorry. And then the ix will go through the Pauli noise channel lambda. We know that it will give you lambda ix times ix. This is because we have seen that before. When you input a Pauli operator into a Pauli channel, it will still give you the Pauli channel, but with a coefficient of Pauli fidelity lambda, depending on which Pauli you input. So here we will get a lambda ix. And then going through the C0 gate, there's something very good about ix, that is C0 will not change ix. So it is still ix. And then it will go through the Pauli gate layer, still be ix, and go through the Pauli noise. It gives you lambda ix square. And similarly, if you go through 3 layer, it will give you lambda ix to the 3rd power. So now this will give us a protocol to learn the Pauli noise channel. It's very simple. So in an experiment, we can just prepare a +1 eigenstate of Pauli ix. And at the end, we do the Pauli measurement of ix at the end. And with some effort, you can work it out, or you can refer to this original paper. The fidelity, the expectation value you get for measuring operator ix will be something like aix times lambda ix to the dth power. Here, aix is something related to the spam noise, and it does not depend on the number of concatenation. And the d is basically the number of C0 you concatenate in the sequence. So you can imagine that if you have this form, you can just do the experiment for different depths d. And you can just do a curve fitting to extract lambda ix. And this will give you an estimation that is spam robust, does not depend on aix. So this is how we use cycle benchmarking to learn lambda ix.
Quick question. The reason you don't have an offset is because you assume you're also twirling, you don't have an offset in this aix times lambda d, is because you're assuming you're also having an extra gate at the end to twirl the readout?
Yeah, exactly. So you see that in this figure, at least this gate is to twirl the measurement, to separation, and this gate is to the readout. So effectively, everything is Pauli. And as you see, there's no bias in this case. Yeah. Okay. Great. However, we want to mention that this method definitely cannot be used to learn all Pauli fidelity, because if you look at Pauli xz, C0 will change xz to yy. Iz, C0 will change iz to zz. So basically, we cannot use ix does not change along the C0 gate. And now we want to ask, can we do some trick to learn the other Pauli? Well, so here will come like the one of the overview of our result. Basically, we see that you can improve CV with some kind of interleaving trick for you to learn more information. We will talk about what does this trick mean later. But basically, the result is that we can learn some individual polyfidelities like lambda ix, lambda zi, and at the end there are 7 of them. And we can learn some combination of some product of polyfidelities like lambda iz times lambda zz. However, anything beyond this is like unlearnable. Basically, for example, individually lambda xx and lambda zz will become unlearnable. Basically, this will come from our main result, like how to classify learnability using a graph representation. But for now, let's first show that how do we learn these polyfidelities. To understand that, here will come like the main object, some of the main graph theoretical tools of our work. We define something we call the pattern transfer graph. So a pattern transfer graph basically just a way to represent how the Pauli operator is being mapped by Clifford gate. A pattern of a Pauli is basically we define to be a cross-graining of a Pauli operator. So for n-cubic Pauli operator, we just replace it by an NB string. How do we do that? We replace every identity Pauli with a 0, and we replace every non-identity Pauli, for example, x, y, z, with a 1. So for 2-qubit cases, we will have like 4 different patterns. The reason why I only care about pattern is because single qubit gate in our case is something like free. We assume it to be noiseless. So in some sense, the Pauli x, y, z does not have any difference. Yeah, but let's just agree with this for now to see how we define the pattern transfer graph. So the edge of the pattern transfer graph basically represents a transformation of all Pauli operators. So let's consider that we only focus on a single CNOT gate. And let's see how CNOT gate would evolve all the 4 to the n possible 2-qubit Pauli operators. So the first CNOT will change ix to ix, right? So we will draw a line, draw an edge from the pattern 01 to pattern 01, which is labeled by lambda ix. And similarly, CNOT will transfer xz to yy. So we draw an edge here because they all have Pauli pattern 1, 1. Similarly for lambda yy. And for lambda iz, CNOT will change iz to zz, which change the pattern. So this will be a line from 01 to 1, 1. And similarly, reversely, we will have a line labeled by lambda zz. And you can do all of them. And at the end, you will see that there are in the end 16 different edges. And here comes our main claim. We claim that the polyfidelities live on the cycle would be learnable. What do we mean? Basically, a cycle can include a self loop. For example, lambda ii, lambda zi, and lambda ix, they live on the self loop, and we claim they are learnable. And also, there could be a length 2 cycle, for example, this cycle. You're going from left to right, you pick up lambda iz, and you're going back, you pick from, sorry. Yeah, sorry, I think I make a mistake here. This one should be, for example, dy, yeah. Sorry about that. Basically, if you choose a cycle like this and you pick lambda iz, pick lambda zy, and product them together, they also be something learnable. And now let's see how we do that. First, let's think about how we learn lambda zx. As we see that CNOT will change zx to yy, but we can still do that with a simple trick. So let's investigate if we input zx here, what will happen. Basically, zx will not change because of single qubit Pauli gate, and zx will pick up a factor of lambda zx, and going through the CNOT gate, CNOT will change xz into yy. And here, once we can do that, we can insert some single qubit Clifford gate, square root x, square root z, square root x, to turn the Pauli operator back into xz. Here, we are able to do that because in our assumption, we assume that single qubit gate, the noise is negligible, right? And similarly, you can do this once again, and when they become YY, you just turn it back. So at the end, you will see that you will be able to get lambda xz to the this power. And for the single qubit ledger, you can just merge them together to still be a single qubit gate. So basically, using this 1Q single qubit rotation trick, we can learn lambda xz in a way that is sparse robust. However, this is the last example. Things become a little bit different if we consider about, for example, Pauli IZ. What will happen if you input the IZ? IZ going through Pauli still IZ, pick up lambda IZ. Now, C0 will change IZ to ZZ. The question for us to ask now is, can we use single qubit gate to rotate ZZ back to IZ? And the answer would be no. This is not possible because you cannot make a Z into I using single qubit gate. Well, one thing we can do that, okay, is now we just give up. We don't do anything. We just input the identity here and see what happened. And now, because we have a ZZ here, ZZ will pick up a lambda ZZ, and ZZ will be turned back into IZ by the C0 gate. So if we prepare IZ, apply even ledger of C0 gate, and measure IZ, we can actually learn the product lambda ZZ times lambda IZ in a spam robust manner. But we cannot learn lambda ZZ and lambda IZ individually. What is the difference in this example? Well, the difference here is that the Pauli pattern is changed by C0 gate, and you cannot change the pattern using single qubit gate. So that is why this IZ to ZZ is different from like XZ to YY. Also, we want to mention that the trajectory of the Pauli operator, how they evolve, will actually form a cycle in the graph. And we can learn, this is how we learn the product of Pauli fidelity along the cycle, right? Lambda IZ times lambda ZZ. To sum up, we have this Pauli pattern transfer graph with 2 to the n vertex and 4 to the n edges for a single Clifford gate. We have an observation. For every, we have already shown that for every Clifford gate, we can learn the product of Pauli fidelities along every cycle in a graph using cycle benchmarking with some trick. So now one question for us to ask is, we know that every cycle is learnable, but is something does not form cycle, is that also learnable? To answer this question, we may ask, what is the dual of a cycle in a graph? And the answer will be cut. So basically, a cut is basically you cut the vertex of the edge into two separate sides, and the cut is where you cut through the edge. So in this figure, you can easily construct these two cuts. So now I will present the main result of our work. I only do it informally. Basically, we have this theorem. In a pattern transfer graph, the product of Pauli fidelities along every cycle is learnable. The proof is just using cycle benchmarking. On the other hand, the product of Pauli fidelity that is not along cycles is unlearnable. This is a bit informal, but I hope it's not understandable. The proof is just that we can, for every cut in the figure, we can induce a gauge transformation that creates some that makes the product not lying in a cycle to be unlearnable. So this result will achieve a complete classification of learnability.
Sorry, can you just give us the example again for the not along a cycle in the previous picture that you had?
Yeah, sure. So we will actually have a cycle for C0 gate, but for now, we can give a quick example. So along a cycle, for example, lambda II, lambda ZI is along a cycle. And for any product going from, so you can understand this edge as a multi-edge. So you just pick one of them. So lambda IZ times lambda ZZ is a cycle.
Yeah, I guess it's the multi-edge thing that I'm trying to figure, because I understand what you mean by cut set and like, you know, they have loops and so on, but this is multi-edge, so it's a little bit funnier.
Yeah, I agree with you. Maybe, yes, because multi-edge is a little bit like, might cause some confusion, but just think of this as a two-edge, and then you pick a cycle. We'll see example in a minute.
So there's two edges there, and I pick one of the cycles, not both. But if I have three edges there, what happens?
I mean, it's not important how many edge you have there. So it's like if you're going from the left-hand side to the right-hand side, you can only pick one edge. And you need to get back, and you pick another edge to get back. And you can do this one more and more. As long as you end up in the same place, you'll get a cycle.
Okay.
Does that make sense?
Yeah, and the cycles are learnable.
Yes, every cycle is learnable.
Right. And the one here that isn't a cycle that I can't go back is which one should I pick, for instance?
There are many examples. For example, if you just pick a lambda iz, then that is not a cycle. And also, if you pick lambda iz times lambda iy, it is also not a cycle. The idea to say what thing is not a cycle will be a little bit more tricky. We have a way to do it like more rigorously. So in the graph theory, they have a way to like equip a cycle or cut to map them into a linear space. And if you use that method, you can really see what we mean by noting a cycle. Yeah,
I see. Yeah. You mean like okay, like I think I understand but for some reason I'm still a little bit confused on picking two here in the picture. So if I pick iz, I can go to 1 and come back through like zy, for instance, and
yes,
right, or zz. I can pick either one. I think, right?
Yes, you're right.
And then I go through ix, and then I can go back through iz. So I have a product of three things. Well, actually, no, sorry, I don't have to go through x. Yes, I have a product of two things.
Yeah. Yes.
Yeah. Right. So I have I have izz and maybe iyzy.
Yes. Yeah.
And
so
one of those you're saying I can break up.
No. If you're going from left hand side to right hand side and go back, you got four possible choices, right? Ix times izzy, izzz, or iyzy, iyzz. But you will see that even though you got four products, like there are only three independent degree of freedom. If you know any three of them, you can get the fourth one. So, I mean, is that your question? So you can learn all the four, but
all the four products.
Yeah, but because they are not give you 4 degree of freedom.
Yeah, they're not independent in some sense.
Yeah.
They give you one, I guess.
Yeah. And to give you one unlearnable stuff. Yeah. So how about the way? Yeah. Thanks for the clarifying question. Basically, I want to say that this give a complete classification of learnability because it's not very rigorous, but giving you the space of all the edge in the pattern transfer graph, you can decompose it as an orthogonal direct sum of the cycle space and the cut space. And for every linear function of the gate noise, you can always decompose the function as some function span in the cycle span space and some parts span in the cut space. And the function is learnable if and only if the function is like only span supported on the cycle space, but have no overlap with the cut space. This might be a bit vague, but we'll see an example later. The point I want to make here is that in our paper, we rigorously talk about the learnability of linear function. But in the case that when the noise is really small, basically every function can be approximated as a linear function of the gate noise because the higher order terms, just you can ignore them. Well, I think it's maybe helpful to just go into an example and to not talk about this or very abstract stuff. So this is a pattern transfer graph of a single CNOT gate. And here we ignore the 0, term because that is an isolated island. We don't have to care about it. And let's see what are the learnable information and what are the unlearnable part of the gauge freedom, right? We first pick everything on the self loop, I think, and this 5 unlearnable. And then we pick up like 2 cycle, lambda iz, lambda zz, lambda iz, lambda zy, lambda iy, lambda zz. And you can also have the first one, but that is not linearly, that's not independent. And also for this edge, you can have these 3. So in total, you have like 13 of them. And now let's consider cut. We argue that for every cut, you can induce some kind of gauge transformation. For example, if you cut here, and we argue that you can do this thing in your noise model. For the lambda iz and lambda yy, you can like increase them by a factor of eta. And for lambda zy and lambda zz, you decrease them by a factor of eta. And also you need to modify the span noise in your circuit like accordingly. We argue that if you do this, this will actually be a gauge transformation. According to the definition later. You can see the detail in our paper. But basically, if you do this, there's no way for you to notice any different here. Not only from a cycle benchmarking protocol, but from any protocol, you cannot notice this difference. This is basically what we prove. And this basically show that there's 1 degree of freedom you cannot learn. And also, if you do a cut here, you can do similar things of increasing xi and yi by a factor and decrease xx and yx by a factor of eta. And this will also like give you an unlearnable degree of freedom. So at the end, for the 15 non-trivial degree of freedom, we can show that 13 of them are learnable and 2 of them are unlearnable. And finally, because with a first order approximation, the Pauli error rates basically can be viewed as a linear transformation of all the Pauli fidelities. So we can rigorously determine which part of the Pauli fidelity is learnable up to first order. And it turned out that there's also like 13 degree of freedoms of Pauli fidelities that are learnable, and we list it here for Senrui gate. Well, thanks to this this characterization of like we make the learnable space to the cycle space, we can also answer the question of classifying like learnable part and unlearnable part. Basically, for an n-cubic Clifford gate, if we, let's say, denote the number of connected components in its pattern transfer graph, then using some graph theoretical method, we can show that the learnable, the dimension of the cycle space or the dimension of the learnable information is something like 4 to the n minus 2 to the n plus c. And the unlearnable stuff is like 2 to the n minus c. So the point is that the unlearnable information, even though it can be exponentially large, it is like compared to the older information, it is only an exponentially small portion. Well, that is just one observation we have. So, and we can also like construct more example with different gate set. So instead of C0, if we consider swap, it will be the pattern transfer graph will be something look like this. And we can also like, for example, combine 2 Clifford gate together to form a gate set and think about what is its pattern transfer graph. And it will be something like this. Here we ignore the self loop for clarity. And we have many of this. And for each of them, we can
have different noise processes for each gate, right?
Yeah, so for each different gate, we need a
different lambda.
Yeah, different lambda. So it's a new set of parameters. For example, you can see that for C0 and swap, we have 32 different parameters.
Mm-hmm.
Yeah, but interesting is a C0 and swap individually have like 2 degree of freedom, 1 degree of freedom. But if you combine them together, basically you only have 2 degree of freedom. There's some correlation between them. And anyway, you can just by counting how many.
Is there a construction you could come up with, or have you proved that there isn't a gate set that would allow me to have 0 UDF?
That's an interesting question. I think it's not possible. So the unlearnable degree of freedom can always be written as, let me see. So here's the point. There do exist gates that give you 0 unlearnable degree of freedom, but that would be something like a trivial gate. So if a gate does not generate any entanglement, then if you look at the pattern transfer graph, every point will be an isolated island. In that case, there's no unlearnable degree of freedom. But this is actually a very good question. If you consider identity gate, right? Identity gate, but with Pauli noise, then everything is learnable. Because according to our theory. And this is also like known in the literature because like in the one paper by Flamia and Woolman, they show that if the gate is identity, then basically every poly fit that is learnable.
Yeah, I think that paper says that, and it's easy to show that you can do the same thing and learn it on with gates, and it doesn't show how. But I don't think that's the case, as you've shown here.
Yeah, so I think that's much more tricky issue when people didn't realize earlier. Yeah,
that's right. But if you take some larger entangling gate set like CNOT swap, I don't know, some other Clifford's things. You think it's probably impossible to find a combination of entangling gates that could give you 0 degrees of freedom, because you kind of show this reduction, right? With if I have CNOT and swap, there's actually less unlearnable degrees of freedom.
Yeah.
So you're saying probably it's not likely that I can find something that has 0 unlearnable degrees of freedom.
Yes, because in the way we construct, basically we can argue that the unlearnable degree of a larger gate set, how to say, the unlearnable degree of freedom cannot be less than their component. Yeah. I mean, so it cannot be 1. It cannot be less than the unlearnable degree of C0. This is something we can prove. I don't know. I don't remember how we prove that, but we can prove that. So basically, if your gate set contains C0 and you assume that every node is independent, then the unlearnable degree of freedom is at least 2.
Okay, thank you. That's very interesting.
Yeah, I think this is the last slide for the theory part.
One quick question: what is Circ 3?
Oh, so sorry, I didn't explain that. Basically, that's a permutation of 3 qubits: permute 0, qubit 0 to qubit 1, qubit 1 to qubit 2, and qubit 2 to qubit 0. So just a permutation, and yeah. Yeah, let me show the last slide of the theory part. This is one part that I really like. The code is why I like the name of cycle benchmarking. Well, so I actually have 2 different meaning of cycles appearing in this talk. The first is the cycle benchmarking. So if you look into the original paper which proposed cycle benchmarking, the cycle in their work actually refers to a clock cycle. Basically, they view application of a multi-qubit Clifford gate and a single qubit gate as a 1 clock cycle, and they do different clock cycle to the benchmarking. So they call it cycle benchmarking. But in this paper, we talk about cycle on a pattern transfer graph. So the cycle here is a graph theoretical sense. But very interestingly, we show that basically cycle benchmarking is just benchmarking cycle in a graph theoretical sense. So you can understand cycle benchmarking in 2 different ways, either in the clock cycle or the cycle in the graph. So that's why I really think cycle benchmarking is a very, very interesting name. I don't know if they already have this in mind when they propose this name. Well, at least the take-home message here is that all the learnable information of the Pauli noise can be learned via cycle benchmarking with some interleaving single qubit gate. That's not that important. Yeah. I think I can stop here because I've already used 1 hour. I don't know if...
Yeah, folks, this is a great time to post questions in the chat, and I'll try to bring them up as we are getting to the end of this. Perhaps we can use some of this time to you can quickly walk us over some of the next data and section that you had.
Yes, and that will be very quick. I just want to show some experimental data with IBM's device.
Great. Maybe one quick question before that. Actually, it's quite relevant. Is learning Pauli noise equivalent to gate set tomography?
That's a very good question. I would say that in some sense, everything you do is gate set tomography. If you want to account for spam noise, everything you do is a kind of gate set tomography. And you can think that Pauli noise model is a specific kind of gate set tomography, or the so-called parametric gate set tomography in their paper. In how the people work on gate set tomography talk about that. Yeah. But the point is that because we restrict to Pauli noise model, we can analyze the gauge like very carefully in a very mathematical way. If you think about very general gate set tomography, I don't think you can obtain this like very elegant result, like using cycle space to characterize.
Okay.
Yeah, that's a good question. Let's do some experimental result. The first result is, okay, we really want to do that in IBM's devices to learn a single CNOT gate. And we use two kinds of cycle benchmarking. The one is the original cycle benchmarking circuit. The second one is like the cycle benchmarking circuit with some single qubit threading. And you see that the second one really help you like learn more degree of freedom. Here, by combining IZ and ZZ together, I mean, I only report the geometric mean of them because they are somehow degenerated together. We cannot learn them individually. Maybe some message to note that is these two methods give you roughly the same average fidelity. And if you look at the individual one, for example, let me see. Here it reports X, Y, and YZ. But if you multiply X, Y, and YZ together here, basically it will give you this guy. So I just want to say that these two are consistent. So this basically tells us that, well, single qubit gate really does not cause much error compared to two qubit gates. And this will give you all the 13 degree of learnable information. And one thing we can do is that we can, because now we have 2 degree of freedom, lambda Z and
one quick comment or question. Just because you get, right, you could have single qubit noise in qubit 1 and qubit 2, so it's purely single qubit noise, but you're going to get an XX term. So just seeing an XX here doesn't mean it's single qubit or 2 qubit noise. It just means that you could have single qubit noise on both acting at the same time. I think maybe that's what
you... Yeah. I think that's a good point.
Doesn't mean it's actually the 2 qubit noise. It could just be T1 on each qubit.
Yes. Just as you say, you're right. Because there's a difference of putting the noise before the gate and after the gate. So it's hard to say it's a single qubit noise or 2 qubit noise, right? Because a single X, if before that is a single X, then after that is a 2 qubit. And vice versa.
Like if your lambda had a tensor product structure, you would still get XX terms, NYY and ZZ, but it's not. I wouldn't call that 2 qubit noise per se. It's just single qubit noise on each qubit.
Yes. I think in some sense,
yeah, because they're independent and it's. Thanks.
Yes. Thanks. And so even though we cannot learn lambda XX and lambda ZZ, we can somehow use a so-called physical constraint, which means basically quantum channel have to be a CBTP map. Then this constraint will give us help us to bound the value of lambda X and lambda ZZ. And it turned out that the bound is something like a rectangle. And using this bound, we can plot all the Pauli error rates in this figure. Basically, the Pauli error rates on the left-hand side of this red line is something that is learnable. And we see that that makes sense. For the learnable one, IX and ZI, the single qubit noise is like very high, and 2 qubit noise is in some sense negligible. But for all these unlearnable ones, it's like not very lucky. Because there is a very large physical region. We cannot decide which part is it. Yeah. And I also want to mention that, just as Lacto also mentioned, you cannot simply say that, okay, we just think that 2 qubit gate is 0 and the XX is 0 and XI is very high. Because of the entangling gate here, that it really doesn't mean that XX is 2 qubit noise and XI is 1 qubit noise, because the entangling gate will make the structure very unclear. One final thing we want to mention is that, can we resolve the unlearnability? Well, the answer should be no, right? Or no, I mean, at least should not be that simple, or I'm wasting time here. So basically, one question we can notice that the unlearnability comes from the gauge freedom. But the unlearnability does not exist if we have, for example, we can prepare any initial state perfectly. Because if we can do that, basically this will fix us to a specific point in the gauge, and we have no room to move in the gauge. Then in that sense, we can effectively fix the gauge and learn all the Pauli fidelities. So basically, we designed a protocol that able to learn the Pauli fidelity if we have perfect state preparation. This is the simulation. In simulation, we show that if we have perfect state preparation at the left hand side, and we increase the measurement error rate, it will still give a pretty good prediction. Here's a blue line, the R prediction, and the red cross is the true value. You see that the true value always lining the error bar, something like that. But if we increase the state preparation error, basically you will give like very, very unphysical and incorrect answer. But there's hope that if our system, for example, our system might be able to prepare state very good. If that is the case, then we can use that to resolve the unlearnability. However, when we apply this to IBM's devices, what do we say that if we ignore the separation noise, our estimate will give us unphysical result. So here the blue region is the physical region we obtained earlier on, and the dot here is what we estimate using the protocol that we ignore the separation noise, and this will give us some unphysical result. This basically implies that the assumption of perfect separation noise is not practical for characterizing single CNOT gate. We can even use the violation of the physical region to calculate a lower bound of the separation noise, which what we obtain is like 0.6%. Think of depolarizing noise. I will argue that this could also come from other imperfectness of the assumption, not necessarily from separation noise. But I think the message here is pretty clear. That is, you cannot simply assume that, okay, there's no separation noise to overcome the unlearnability issue. So yeah, that is the message here. So let me just use the one page of Outlook. After I finish that, I can take any last time question. Okay. So just to make a summary, in this work, we discussed the issue of learnability of Pauli noise. The main result we have is that the learnability is fully characterized by the cycle space of a so-called pattern transfer graph. And I put my favorite pattern transfer graph here for CNOT. And cycle benchmarking with some little trick can learn all the learnable information. And at the end, we experimentally show that the issue of unlearnability is experimentally relevant. Maybe in the future, we have a way to prepare state like perfectly. Then we don't have the issue of learnability. But at least for now, it is still a practical concern. So for future direction open question, there are several of them. For example, the first will be the practical implication for quantum error mitigation. Like Zach mentioned, how would this really affect the probabilistic error cancellation method? I'm not sure what is the answer. And we haven't talked about the time and sample complexity for learning. I have a recent paper talk about the sample complexity of learning polychannel in a black box model, but maybe we can generalize to this model like polychannel attached with quantum gates. And finally, is there other way to resolve the unlearnability using other techniques? For example, quantum non-demolition measurement. In our model, we prepare once and measure once. Maybe you have some mid-circuit measurement. I don't know how to, but maybe you have a chance to overcome unlearnability. Well, but with this, I would like to thank you for your attention and take any questions.
Senrui, thank you very much for the wonderful talk, and congratulations on the very nice results again. Folks, feel free to post any final questions here. I know we had quite a lot of questions, so we'll keep this pretty short. One quick question from Ron: is the code for the experiments with IBM available with the paper?
Yes. Yes. We can make it available. For now, we haven't really put it on the GitHub. We want to do that. Haven't done that. But if you want, you can send me a request. I'll give it to you. Yeah.
Okay. Excellent. I have quite a few other questions, but maybe just in the interest of time, I think maybe Senrui, I'd like to leave you with a chance to share with us any final words, messages, take homes, etc.
Yeah. I think the main take home message I would like to give is like cycle benchmarking can really be understood in two ways. I mean, cycle benchmarking can benchmark cycle. That's the most interesting thing I think from this work. Yeah.
Excellent. Well, Senrui, thank you so much. Great talk. Folks, thank you for tuning in and for all the discussion and questions and keeping this fun and light and active. This talk will stay recorded, so you can go back and rewatch it. But if you want to be able to discuss and interact live with our speakers, tune in next Friday at noon Eastern Time.
Yeah.
Have a great day.